Okay, so still more on expansion work, but now let's get into reversible expansion, okay? And here, this is where the equations are still going to be simple equations, but in the world of thermo, it's the language that gets tough, okay? So let's first by defining what reversible means in thermo. It's a change that can be reversed by an infinitesimally small variation. And a good example of this is thermal equilibrium. So suppose I have two chambers, okay, and suppose they're separated by a diathermic wall, okay? Well, if this chamber is at T1 and this chamber is at T2, we recognize that energy or heat will flow, okay, between those two devices between those two chambers, if T1 does not equal T2, okay? And so if T1 does not equal T2, then heat will flow depending on which way it needs to, depending on which one is greater, right? Heat will flow from the hot object to the cold object, okay? And using this kind of language of calculus, and I don't want you all to be too terribly concerned or confused by this, but all this is saying, by saying this is reversible, let me finish writing this relationship, T2 plus or minus dT2, which is much greater than that absolute value. So all that it's saying is, okay, this infinitesimally small variation, that's what it is. Okay, so T1 plus or minus dT1, that's this infinitesimally small variation. And because that's infinitesimally small, this quantity is going to be much, much greater than what that change is in the first place, okay? So reversibility means simply if T1 becomes just slightly warmer than T2, it becomes slightly greater in temperature than T2, heat will flow this way until both of them are at the same temperature, okay? Same with T2, the opposite is true, okay? So now, what about reversible expansion work? Okay, let's keep going with that. So dW equals negative P external dV, and I'm going to define that as irreversible. I can't spell right now. I just got blanked out. I'm listening to my son yell and scream and play outside. I don't know if you guys can hear that or not. As a parent, you can like hear your child yelling from any distance away. Okay. Irreversible. Why did I write irreversible on that equation right there? So remember, this is the equation for expansion against constant external pressure. Let's back up to that for a second. Okay, with this picture right here, right? Whether I'm going expansion or compression, either way, once my system achieves mechanical equilibrium with the surroundings, that means the pressure inside the system will be the same as the pressure of the surroundings. So now there's no more difference between the pressure of those two areas. And so there's going to be nothing that allows it to become reversible unless, of course, I do some type of chemical reaction in here that generates pressure, but that would no longer be expansion against constant external pressure. Okay? So it follows that expansion against constant external pressure is always irreversible. Okay? So how do I write reversible expansion? Well, I can simply say dW equals negative P dV reversible, assuming I can spell. And thus, we have to think of how P depends on V in the reversible expansion. Okay? So in other words, when I calculate irreversible expansion, so I should have left myself space. I'm going to draw an arrow down here, okay? To calculate irreversible work, we just recognize it's simply work equals negative P external times change in volume, okay? To calculate the amount of irreversible work. And we should also recognize that this is in the unit Pascal, and that's in the unit cubic meter, then I will get a joule. Okay, don't forget the dimensional analysis units. Okay. What about calculating work for reversible changes? Aha, well what I have to do is the following. Work equals negative integral P dV integrated from volume initial to volume final, and I can't pull the P out of that integrand. I have to actually integrate it, okay? So that represents, as far as calculation, how we calculate the work done reversibly versus how we calculate work done irreversibly, okay? So let's keep going and do